This is going to be our second set of notes. So just real quick, electric forces, right, our electrostatic forces and the force of gravity, they like you to compare them a lot. Not a lot, but you'll see a multiple choice question in there about it, or possibly, a part C of a free response question. But we've got our electrostatic force equation that we've been using, and now we have the force of gravity, right? You could use that equation. We used this in the first semester briefly, where G is our gravitational constant, right? Our M are the masses of two objects, and R is that distance. So things that you need to keep straight between the two, right, is that gravity is always attractive. Masses always pull each other towards one another. So if you had two objects with mass, the force of gravity is always going to attract. But if these two objects were both also positively charged, the electrostatic force could actually repel them from each other because they're the same charge. So gravity always attracts, where electrostatic forces can attract or repel, based off of their charges. Now, gravity is always much, much weaker than electrostatic forces, which I'm going to prove to you in a second. But gravity has a greater range, right? Gravity can hold planets in orbits around stars, where electrostatic forces hold electrons in clouds around a nucleus. They don't hold anything like that in that massive in any sort of orbit like that. Electric forces also can be shielded or blocked, where gravity cannot be shielded or blocked. I do suggest that you read the examples here, pause the video real quick, but I'm just going to prove to you real quick that gravity is much weaker by looking at a hydrogen atom that's made up of a proton in the nucleus and one electron in its electron cloud. So this math here goes through and shows you that if you take the mass of a proton and the mass of an electron and the distance that separates them, this is the force of attraction between that electron and proton. You can see it's pretty small. But if we put in the charge of a proton and the electric charge of our electron, with that same distance that separates them, you can see that this force, although small, times 10 to the negative eighth here, is much, much stronger than the force of gravity on them. Meaning, if you went back to here, this force of gravity that attracts those two positive objects is so much weaker than these forces that are repelling, that these two objects would repel and accelerate away from each other. They wouldn't move towards each other, right? And that's only if they're charged objects. So just nothing big, but just something to keep in mind, right? That force of gravity attracts, electromagnetic forces can attract or repel. They're both inverse square laws because their forces are inversely proportional to the distance squared. But electromagnetic forces are strong compared to the force of gravity. Let's move on to our more complicated problems here. The superposition principle. Basically, what it means is that forces can pull in multiple directions, and the resultant force, right, is the vector sum of the forces. So basically, we know if I pushed an object to the right with a force of 1 Newton, and you also pushed to the right with a force of 2 Newtons, that the net force would be 3 Newtons, right? It's the vector sum. Or if it was 1 Newton and someone pushed the opposite way at 2 Newtons, then the net force would be negative 1 Newton because, right, negative 2 to the right, positive 1 to the left. And remember that if we were to push something with 4 Newtons to the right, but also push up with a force of 3 Newtons, then the vector sum would be our a squared, right, plus our b squared, and that would equal our c squared. That's all we're going to do here is we're going to have multiple charged objects. We're going to have to figure out if the charged objects apply forces in the same direction, we add them together. If the charged objects cause forces to be in opposite directions, then we subtract them. And if they're at angles, we use our right triangles to figure out the total force on them. So here's our first example. We have 3 protons grouped together. So we've got this point charge, remember, and it is 3 protons together, which means if one proton is 1.6 times 10 to the negative 19th, then it's 3 protons, so we multiply that by 3, and we know that this is a positive, right? What would that be? 4.8 times 10 to the negative 19th coulombs. It says we have 2 more protons, right, in a group 8 millimeters to the right. So 0.008 meters to the right, there is another group of 2 protons. So that is positive 3.2 times 10 to the negative 19th coulombs. And then there are 5 electrons, so we know it's negative 12 millimeters to the left. So all the way out here at 0.012 meters, there are, what did we say, 5 electrons. So 1.6 times 10 to the negative 19th times 5 gives us, what, a charge, I believe, of 8 times 10 to the negative 19th coulombs. And we want to know what is the net force on the 3 protons in the middle. Well, let's call this Q1, Q2, and Q3. And so what we need to do is we need to look and say, okay, well, what force does Q1 and 2 apply to each other? And because we want the force of 1 and 2, we need Q1 and Q2 and the distance between 1 and 2 squared, right? Now, we know that Q1 is attracted to Q2 and Q2 is attracted to Q1, which means this force of Q1 is pulling, right, or sorry, Q2 is pulling Q1 to the right, and Q1 is pulling to the left, right, Q2 to the left. Now, we really don't care about this force because we only want to know what's the force on the middle 3 protons. Now, those forces are the same, so we're really going to find both of them, but we really only care about that force on Q2, which is pulling to the left. So we put in our values, right? 9 times 10 to the 9th is our constant. Our Q1 value, we said, was 8 times 10 to the negative 19th. We're putting in the absolute value, right? Not the negative. Our Q2 is 4.8 times 10 to the negative 19th, right? Because it's made up of those 3 protons. We divide it by the distance between them in meters, 0.012, and we make sure we square that value. Now, I know that Q1 is pulled to the right, but Q2 is pulled to the left, right? Then that's what we care about, and we know it's pulled with a force of, when we put that in our calculator, 2.4 times 10 to the negative 23rd newtons. So now we care about, right, the interaction of what does Q3 do to Q2? Well, we know that Q2 and Q3 are both positively charged, so they repel each other. So that means that Q3 is going to be pushed to the right, but we don't care about that. We care about that Q3 is going to push Q2 to the left, right? Those 2 forces will be the same, but we don't really care about that force. We care about what it does to Q2. And keep in mind that Q1 and Q3, just because Q2 is in between them, it doesn't matter. Q1 is still attracted to Q3, so it would be pulled to the right towards Q3, and Q3 would be pulled to the left towards Q1, but they don't ask us what the charge is, what the force is at Q1 or Q3, so we don't care, right? We're only focusing on these forces on Q2. So we want to find that force, so we want to find the force between charge 2 and 3. So 9 times 10 to the 9th, put in the charge of 2, 4.8 times 10 to the negative 19th, put in the charge of our Q3, right, our 2 protons, so 3.2 times 10 to the negative 19th, over the distance squared, 0.008 squared, and that gets us that is also to the left, right, and it is 2.16 times 10 to the negative 23rd newtons. Well, we want to know the net force, right? Well, the net force on Q2 is force 1, 2 plus force 2, 3. Now, force 1, 2, we said on charge Q2 is to the left, so we're going to say it's negative, right? 2.4 times 10 to the negative 23rd from here. And then force 2, 3 is also to the left, so we're going to say it's negative, right? 2.16 times 10 to the negative 23rd. When you add those together, because they're both negative numbers, you get negative 4.56 times 10 to the negative 23rd newtons, right? So there is a net force to the left on charge Q2 that's pushing it to the left of 4.56 because it's being pulled to the left because of Q1 and being pushed to the left because of Q3. You'll have a couple of those types on your homework, and then we will move